So now I begin with the things which I wasn't able to finish last time. This is about Cartan subalgebras of Lie algebra. I hope that you still remember what it is, but I will say this. So you have what? You have a Lie algebra G. You have a nilpotent subalgebra, and then you consider the corresponding weight root decomposition for this. So alpha and zero roots, G alpha, and here G alpha is the set of those G. First of all, alpha is a linear form on H, and G alpha consists of those G for which add H minus alpha of H to some big power. For example, the power could be taken a dimension of value, OG. G is 0. Then G0 is subalgebra. Actually, we proved last time a very simple relation for the commutators. Here, this notation, I assume that if alpha is not a root, then G alpha is just 0. A root means that this space is not 0. And then G0 is subalgebra, according to this, which can be written as this. This contains H, and moreover, it contains any nilpotent. If a nilpotent subalgebra of G contains H, then it's also contained in G0. So G0 contains any nilpotent subalgebra of G which contains H. This shows in particular that G is not necessarily equal to H, it may be bigger. But still, if G0 is equal to H, then H is called a Cartan subalgebra, some people say Cartan algebra, in G. This is my series of definitions, and other inquiries about this. No inquiries about this. Then last time, I don't remember how much I said, but I will anyhow repeat everything. There are many Cartan subalgebras in any Lie algebra, and actually there is a very good description of all of them. I will not prove this much, but I will give you three things. First, construction of many Cartan subalgebras in an arbitrary algebra. This is one thing. The second thing, I will mention an exercise that which gives an additional description of them. Well, exercise I will formulate. And the last thing, I will formulate a statement about the whole amount of Cartan subalgebras in a Lie algebra, which I will not prove. Proof is contained in particular in the book of Rajan. It is not hard. Simply with this quarter system, courses are very short, so I cannot say anything here. So first of all, definition. An element G and G is called regular. In the following case, I consider the space. You understand? So I consider add the operator at G. It acts on G, and I consider the important part of this operator. You already understand. The space, not the operator. So the space on which this operator is important. This is this. This is a space. Has dimension. And my requirement is that this dimension is minimal. This is a function on the Lie algebra, right? With non-negative, actually positive, because G itself is always contained in this. So it is not zero. This space is not zero. It is a function with positive integer values. And of this value, there is a minimum value. So those elements of the algebra for which this dimension is minimal are called regular. Certainly this is an obliging term, because regular means that a decent element in G should be regular. Irregularity is something which is normally avoided. At least I think so. Yes, actually, almost all elements of Lie algebra are regular. I will formulate right now a more precise statement. But first, let us consider an example, and you will say everything. If G is the Lie algebra number 1, I mean G, L, and C, the Lie algebra of matrices, n cross n matrices, over complex number, the whole theory is over C. Some parts of it are actually valid over R. I don't bother to specify this. So consider the Lie algebra of all matrices. Which elements are regular? And the answer, it is an exercise, so I will not prove it, but it is very simple. The answer is very simple. Matrices have eigenvalues. It's very common for them. A matrix is regular if all eigenvalues are different. Power is different, no multiple eigenvalues. For example, the identity matrix is very much irregular. For the identity matrix, this will be the whole G. Yes. And it is easy to believe that almost every randomly chosen matrix doesn't have multiple eigenvalues. Now, in general, so almost is regular. Take an element G in G and consider the operator at G, commuting with G. G into G. It is an operator of the space and has, as an operator, it has the characteristic polynomial. Lambda to the power m. M is of G plus Pm minus 1 of G lambda m minus 1 plus so on plus P1 of G lambda plus P0 of G. Remark number 1. Obvious. This is 0. You see, this operator has a kernel. G belongs to the kernel. G itself. Right? By this reason, so there is a vector with 0 eigenvalues, so 0 is a root over recursive polynomial, so P of P0 of G is 0. The second statement, which is also obvious, that actually all these functions, P1, P2, P3, are polynomial functions. After all, what? what is at G? At G is a linear map of G into the space of all endomorphisms in G, right? And endomorphisms of G do have characteristic polynomials, and definitely these characteristic polynomials endomorphisms of G is just matrices, and characteristic polynomials, their coefficients are polynomials in matrix entries. It is sort of obvious and very important. So all these functions actually are polynomial functions on the linear space G. Now take L, minimal L, say that PL is not identically zero, so there exists a non-zero value. After all, the leading coefficient is 1, so there should be such a coefficient. My claim claim number 1, G is regular if and only if, let me write it, G this PL of G, the first non-zero coefficient, first from the right, non-zero coefficient of the characteristic polynomial, it is a polynomial function on G, not identically zero, as it was said. So where it is not zero, G is regular. And it's obvious, after all, what is the dimension of G? Well, this space, G0. It is just the multiplicity of the eigenvalue 0 for the transformation at G. So precisely this minimal dimension is L, and minimal dimension is L, and it is L precisely if this polynomial, the multiplicity of root 0 for the characteristic polynomial doesn't exceed L, so PL this coefficient is not 0. So you see, I don't know which language you prefer. You can say, just to sound more in a more sophisticated way, that the set of regular polynomials is a Zariski open set. The set where some polynomial is not equal to 0. It's almost everything. So complement to an algebraic surface. Yes. Now my claim, I will not use it, it's simply important to know that there are many regular elements. And my theorem says that if G is regular, then this thing is a Cartan subalgebra. Back to GL, back to GLN. Again, it is an exercise, I'm not sure that it's formulated this way, but everything is clear. So a regular element is a metric, is a transformation with different eigenvalues. Then there exists a basis in which the matrix is a diagonal matrix, basis composed of eigenvectors. The diagonal entries are lambda 1, lambda m, all not 0, right? Lambda n, GLN C. What is, in this case, GG0? This transformation, add this matrix, is the diagonalizable transformation. So simply we need to know its kernel, and the Cartan algebra becomes the space of matrices which commute with this diagonal matrix. Diagonal matrix with all diagonal entries 0, matrices which commute with it are precisely matrices which are also diagonal in the same basis, maybe with repeating diagonal entries, right? The dimension is equal to n. So a Cartan algebra becomes simply the following thing. We choose a basis in our space and then consider all elements of our Lie algebra, which in respect to this basis are diagonal matrices. So such a space with diagonal matrices. There remains a spaces because we can take different bases. But these are precisely Cartan algebras. I say precisely, although my theorem says only that they are Cartan algebras. Actually, they are precisely Cartan algebras. So this is a theorem which I'm going immediately to prove. Do you have questions now at this moment? At this moment, you don't have questions. Maybe we'll have them next moment. The proof is not hard. Look, I consider first a very much stupid algebra H. Just H. So I fix a G, a regular element. H is just CG. So one-dimensional algebra spanned by this element, and I don't think that you have serious doubts that it is nilpotent. Yes. Still, H is H. So G becomes G0 plus what? Plus the sum of these G alphas with non-zero roots. And this I want to denote separately as G tilde. So this is G0 plus G tilde. G0, yes, is this thing. And G tilde is something. Now, definitely a commutator of any element of G0 and any element of G tilde belongs to G tilde. So that if some H, some eta belongs to G0, then I get a transformation as, well, let me take C. Right? Again, transformation is transformation. So I can consider P, the function P, on G0, I write P of C is equal to the determinant of the characteristic polynomial of L. See, but now C I consider the transformation in G tilde, not in. What about this function? Again, a polynomial function. Determinant. But still, what? Your question? I see. Still one important thing. What do you think of P of G? I personally think it's not zero. Look, what is G tilde? It is the union of all G alpha with non-zero alpha, right? Precisely means that it consists of non-zero spaces, spaces corresponding to non-zero eigenvalues of at G, right? So G at G definitely acts as non-degenerate operator on G tilde, right? Precisely by definition. So P of G is not zero. But if P of G is not zero, and P is a polynomial, then we need to admit that P very often is not equal to zero. Consider the set of all eta for which P of eta is not zero. The subspace of G0. And since P is a polynomial function, and it is not equal to zero at some point, So this is again a very big set. A dense open set of which there's a risk open sets for almost everything, right? Dense is sufficient for me. So this set is dense in G0. Now, take some eta in this set. Then again, we must admit that add eta is on the J rate, right? Because the determinant of critical lemma is not 0. If so, this means that the space G eta 0, the 0 space for eta, is totally contained in G0, which is G0. But if you consider this inclusion, you immediately see one thing. After all, for G this dimension was minimal. How it is possible that for some other element of G, d eta 0 is contained in it? Dimension of that can be less than dimension of that. The same maybe, but then it is the same. So this means that G eta 0 is equal to G0, right? Well, this is something very strong, because this means that for every element the operator at eta at G into G is nilpotent, right? No, G0 in G0 in 0 is nilpotent, right? If it is nilpotent, when P of eta is not equal to G, then it's nilpotent, always nilpotent. You see, if we have an operator which depends continuously on a point in this space G0, and yes, and also it is true for any, it is nilpotent for any element in some dense set, then it will be nilpotent everywhere. Nilpotence is a property, a continuous property. So if it holds for a dense subset in G0, then it holds for every element in G0. And we get our almost final result. We see that not d eta, that G00, the G00 is contained in G0, right? A very strong statement, because this is what? This is G0, right? Or I can say GH0. But H is a part of this. So actually, this is contained in this. Smaller algebra, bigger G0. And this altogether shows that this is equal to this. Since we have inclusion in both directions, this is obvious. And this is what we proved. Yes, so this is a Cartan algebra. For as soon as we take any regular element. Let me say something about this. I will not even write anything. First, it is true that if a Cartan algebra contains a regular element, then it is this. If a Cartan algebra contains a regular element G, then it is G0. It actually is contained in our proof. I will not specify. It is an exercise. This implies, by the way, that if two Cartan algebras share a regular element, then they're the same. Right? One more lemma, which is actually true, that any Cartan algebra, whichever you take, contains at least one regular element. As soon as you have this, you see that actually all Cartan algebras are obtained by this construction. The proof of this statement, that every Cartan algebra contains a regular element, is more or less the same, at least by sight, as the proof which I gave to you. Again, you play with characteristic polynomials, there is open sets and everything. I will not do it. I will not need it. One more thing. The last thing about the Cartan algebras, which I'm going to say here. There are many Cartan algebras, maybe. But if your Lie algebra is a Lie algebra of a Lie group, this Lie group acts in your Lie algebra, a joint action, big L. This action takes Cartan algebras into Cartan algebras. And actually, it acts in the set of Cartan algebras transitively. So we need to take just one Cartan algebra and to apply to it all possible transformation from the Lie group. And you get all Cartan algebras. These results are proven in many places, in particular in the book of Vardarajan. I will not prove them here. I will not be able to use them. Yes?
So there's examples of Lie algebras not derived from Lie groups where there is no transitive action between Cartan.
But still, do you mean finite dimensional case? Then there is a theorem.
That's my first question.
In the infinite dimensional case, the whole theory is transformed a little bit. Yeah. Yes, but in the finite dimensional case, every finite dimensional Lie algebra belongs to some Lie group. So it's always true.
One more thing.
Yes.
When you do take a different Cartan subalgebra, I guess that you get the same weight spaces.
Oh no.
No.
Weight spaces are also transformed by the same transformation L. Okay. In particular, G0 is the Cartan algebra. So you take different Cartan algebra. Weight spaces are the same in the sense that there are the same weights.
Yes.
Weights. In what sense the same? Weights are defined on the Cartan algebra, so the same in some sense of some isomorphism in Cartan algebras. But still, well, the composition, this weight decompositions, root decompositions are very similar. They're taken into each other by the transformation of the embedded group. Yes. I don't think we can say more. Actually, I will need the theory not in this generality. I will apply it to the semi-simple case, when in particular all Cartan algebras will be not just nilpotent, they will be commutative. And actually, if G is a semi-simple Lie algebra, then there exists a different definition of Cartan algebra, which many people know. It is a maximal commutative subalgebra which contains at least one regular element. If you have a subalgebra of your Lie algebra, which is maximal commutative, that is commutative and is not contained in any bigger commutative subalgebra of Lie algebra, and also contains at least one, it is important, contains at least one regular element, then yes, then it is a Cartan algebra. If you drop this condition that it contains a regular element, you can find algebras, maximal commutative algebras with much bigger dimension. It is easy to understand, simply playing with matrices. Yes, so regularity is important. Well, now I want to make the following thing, an announcement. My next subject here in this class, which I have to make as short as possible, as brief as possible, is Lie algebra cohomology. My notes, of which you have new version sent to you this morning, contain much more about the Lie algebra cohomology than I'm going to say. In particular, many exercises, which I will maybe even I will make actually brief observation, brief account of these exercises, even beginning now. But what I cannot avoid this subject, because I need precisely one, but very important, application of it. The application, I can begin with this, is the so-called while theorem, which says that every finite, well, I do not pronounce the word finite dimension, but I always mean it. Every representation of a semi-simple Lie algebra is decomposed into a sum of irreducible representations. Something which is not true even for GLN. For SLN, yes. This theorem actually is cohomological theorem. And however you prove it, you shouldn't avoid cohomology. In textbooks, and also in my notes, there exists another more or less common application of the cohomology theory, the so-called Levi decomposition. It is an algebraic theorem. I will formulate it without comments, but it is formulated and proven in my notes. If you have a very much arbitrary complex Lie algebra, then, this you know, there is radical, solvable ideal. You factorize over the radical, you get a semi-simple algebra. So actually it's always true, without any cohomology, that any Lie algebra contains a solvable ideal with the quotient being semi-simple. The additional fact is that it is a semi-direct product. That is, this semi-simple Lie algebra has a map, can be embedded in the initial Lie algebra. So my Lie algebra G contains two subalgebras, a radical and a semi-simple algebra. And radical is an ideal. The semi-simple is not an ideal in general, but it is a semi-direct product in the sense which I said. So there are two subalgebras as a vector space. Your Lie algebra is the direct sum of them. As a Lie algebra, not quite a direct sum, because if you take an element from each, from the radical and from this semi-simple Lie algebra, and take the commutative, it will not be zero. It will be an element of this of the radical. Radical is an ideal. Yes. Also a cohomological fact. There are other cohomological facts, but I mention this too, and the first of them will be, we will have to know it. It is something which is very important, after all, simply very important, that for semi-simple Lie algebra there exists this decomposition. Every representation is the direct sum of irreducible representations. So basically the classification of representations, finite representations of semi-simple Lie algebra is reduced to the classification of irreducible representations. And all the rest just obtained by direct summation. Maybe I need to mention, maybe not, that even if your semi-simple Lie algebra is finite dimensional, but the representation is infinite dimensional, this is not true anymore. It is not hard to construct a representation of very common simple Lie algebras. When somebody says this very common, it always means that it is SL2. There are infinite dimensional representations of SL2C, which actually are not direct. The fact is that there is a finite dimensional finite codimensional subrepresentation whose the quotient is not embeddable in your representation. This is what happens. Now cohomology. I will begin very much traditionally with a precise definition. And if it seems to you too complicated, it is not actually. But if it seems to you too complicated, you shouldn't be desperate, because actually in this generality I will never use it. So I have a Lie algebra. Now I don't need algebraic closedness. I wanted to mention two more things. 2 or 3? Let's count. First is the least important. There is one more subsection in my notes between what I said and the cohomology about some additional properties of roots. I don't want to discuss them now. I will discuss them when I know. Logically, they should be here because they precede. They actually should go before cohomology. They are not related to cohomology, but I will discuss them with you when I need them. So this I simply skip. Second thing, a very sad circumstance. By your insistence, we will have a test next Friday. I will give you very simple problems. The material is what we are now. So I believe it is page 39 in my notes. Everything which goes before this page, I mean the latest version. And whatever I say today and on Wednesday is not included in the test. So no cohomology. My test will consist of simple problems. I'm not going to prohibit that you take my notes to the test. And actually, if you know basic definitions, very basic definitions and very basic properties, you will be able to do all this immediately. The only difficulty is that I will give you 5 problems, 50 minutes, and whoever can divide 50 by 5, rather short actually time. Well, whatever you do, I will be satisfied. And the last thing, I often do this, and I will do this now. On Thursday, the day before this test, in the late afternoon, I cannot do it before. I could say 3 o'clock, but actually at 3 probably I will not be able to come at 3. At something like 3:30. I will come to my office, and in the unlikely event that some of you have questions, and in still more unlikely event that I am able to answer these questions, I will help you. So next Thursday, my office, and after 3, approximately 3:30. If you are going to come, but you cannot be in time, because actually if I come and nobody is there, I wait some reasonable time and then I leave. But if you are going to come, but later than 3:30, reasonably later, not at 8, then just send a message to me and I will wait for you. I think all the 3 things, I didn't count them. I said so. If you don't have additional questions on this subject, I will continue.
You said
Yes, Paige.
You said next Friday, right? Not like a couple days from now?
February 14th. I always have this difficulty with next Friday, this Friday, last Friday.
I understand.
But I mean the Friday 4 days from now.
Okay.
Very reasonable question. Thank you, Paige. But more questions. By the way, I sort of know all you, but I also know that some of you are not registered for this class, maybe. I don't know who precisely. It's absolutely the same for me. If you're not registered for the class but still want to come, write this test. I will do everything. I will read it, I will return it to you, I will do everything with the only exception that I will not be able to assign any grade to you after the class is over. Now, if you don't have questions, the cohomology. We can see the following. So it is better to say that everything is finite dimensional, although now it is not so important. It is the definition makes sense. Simply it becomes sort of stupid in the infinite dimensional case. So G is a Lie algebra. And rho is representation. In some space V. Sometimes I will denote this representation as rho, sometimes as V. Now I define a new space. C, Q, G, V. This is the space of all Q-symmetric Q-linear forms on G. With values in V. That's all. In this theory, the terminology is borrowed mainly from topology. So the elements of this space are called cochains. The word cohomology also probably was first used in the topological context. Now I define by a formula which you can think this is complicated. The operator delta, which can be called differential, which can be called coboundary operator, also comes from topology, which is defined by the following formula. I consider element C in CQ. I apply delta to it. Sometimes it's called delta Q. And this will be a cochain from CQ plus 1. So it should be applied to Q plus 1 elements of G. It is equal by definition. I take the sum. For all pairs of these things. Here I write something to make it symmetric. I apply C. I take GS, G the commutator, and the remaining G's, certainly with S and T missing. Minus I write GU and apply it to C with U missing. Actually, very natural. What can I do if I have Q plus 1 arguments and I must deal with them using a function of Q arguments? Either I take 2 arguments and make one out of these 2, for which I have only one tool, the commutator. Or I just drop one, but I cannot drop it altogether because I want to have something multilinear. So I just place it here. I apply it to the result. So this is the formula. Now, as an apology to this formula, I want to make 2 simple statements. First, for some of you this formula can seem, some of you may think that this formula is too abstract, and some of you can think that this formula is not sufficiently abstract. I want to say something to both categories if they exist. Too abstract. You know, this is not an abstract formula. The formula comes from analysis. If you have ever seen a formula for the differential forms, so-called Cartan formula, then you can know that this is actually the same formula. A differential form is a multilinear function of vector fields, and so on and so on. And the same is true for the differential. There is one more actually analytic way to describe this, but without this term. Without this term, it means that the module is trivial. This is always 0. Then you can do the following. What is, after all, after all, elements of a Lie algebra? They can be regarded as, say, left invariant vector fields on the Lie group. Then, as soon as you have this multilinear function, CQ, it is the same as the left invariant differential form of degree Q on the Lie group. Then it becomes the usual differential. Again, for this formula is well known in the Lie theory, in the geometric theory of Lie groups. This is for those who prefer to have more down-to-earth explanation. For those who prefer to have some more, how to say, up-to-sky explanation, I can say that certainly this is a stupid formula. Because homology is a notion from homological algebra. I will give a course in homological algebra next quarter, all are invited, and then certainly we will not consider such stupid formulas. There is a very general definition of homology based on the notion of a resolution. To define homology, you need to consider something which they call a resolution. As soon as you have this resolution, all homology are defined by very short formulas. This comes from what? There exists some canonical way to construct this resolution in the category of Lie algebras. And this is precisely what we do. Certainly the formula become longer. Because this is, you understand, precisely that you fix something which shouldn't be fixed. It should be arbitrary. And as soon as you fix it, you need some formulas which describe this fixation. And they may be long. I want to use the remaining 2 minutes for the following. I didn't say what homology is. So the fact is that this differential, the square of this differential is 0. All differentials have this property. So delta q plus 1 is 0. This can be directly verified for this formula using the Jacobi identity, nothing else, and commutativity. This means that kernel of delta q is contains image of delta q minus 1. Maybe it's better to write it this way. This means that you can take the quotient, which is called HQ of GV, and it's called Q's homology of G with coefficients in V. The terminology is, again, topological. Elements of kernel of delta Q are called cocycles. Elements of image of delta Q minus 1 are called coboundaries. What you take, two cocycles are homological if their difference is a coboundary, and we consider the set of classes of all cocycles with respect to this equivalence relation, and this is what, this comes from topology. This is what homology should be. Yes, unfortunately, today I won't be able to say anything else, so we stop at this moment.